Okay. So today we'll start the next content, that is optical fibers. Okay. So lasers, I think we have completed. We have seen the characteristics of laser, right? So there is spontaneous and stimulated emission of radiations, metastable state, population inversion, lasing action, and working principle of Luby laser, and the working principle of helium ion laser, and other is the applications of laser. I think we have seen all this. Am I right? Am I right?
Yes.
So today we'll start, that is the next part of this module, that is called the optical fibers. Okay. Now let us see some of the fundamentals regarding the optical fibers. Okay, so the fundamentals that are residing to understand the optical fiber is the total internal reflection. So people, you might students, you might be having the idea of total internal reflection. Am I right? You all know what is total internal reflection. Do you have any idea? You have studied in your lower classes about the total internal reflection. Am I right?
Yes, sir.
Right. So
Yes, sir.
can you tell me something regarding total internal reflection? What is total internal reflection? Because total internal reflection is the basic principle for the construction of optical fiber, for principal working and construction of optical fiber. For working of the optical fiber, total internal reflection is the basic principle. Okay. So please let me know what is total internal reflection. Anybody?
It's complete reflection of light within the medium.
Complete reflection of light
Within the medium.
within the medium. Right. Okay. So any other answers I can expect? Any other answers? Total internal reflection. What is the principle of optical fiber? The principle of optical fiber is the total internal reflection. We have two mediums. One is the optical rarer medium and other is the optical denser medium. Right? We have two mediums, right? Where the refractive index changes. What do you mean by refractive index? Refractive index is nothing but the ratio of the velocity of light in one medium to the velocity of light in another medium. Okay, right? So this is a fundamental parameter, that is refractive index, right? So refractive index is defined as the ratio of velocity of light in one medium to the velocity of light in another medium. Okay, so that is what the refractive index. Now if you take two mediums, that is optical rarer medium and other is optical denser medium. Okay, so how the total internal reflection principle takes place? How the total internal reflection takes place if you are having the optical rarer medium and optical denser medium? Can anybody tell? Can anybody tell how the total internal reflection takes place when we have two mediums? One is optical rarer medium and other is optical denser medium. Yes? Anybody? Will anybody give some idea? Or anybody having certain idea behind this?
Sir, the light coming from the optical rarer medium will not be refracted to the optical denser medium, sir.
Once again, beta, once again, please. Once again, the light coming
the light coming from the optical rarer medium will not be refracted to the denser medium.
Are you sure?
Yes. Yes, sir.
Think once again. Think about it once again. We have two mediums. Okay, we have two mediums, right? Wait, I'll see. Just now, see here. I am trying to show you. See, so this is one separation. This is optical rarer medium and this is optical denser medium. So according to you, you tell me now, this is your optical rarer medium and this is your optical denser medium. Now tell me now, how can you give the nomenclature behind that? Make it fast. Make it fast. We have two mediums. One is optical rarer medium, another is optical denser medium. So from where the light should pass? From where? Somebody were telling, right? Somebody were telling it.
Rarer medium, sir.
So this is your rarer medium and this is your denser medium. Are you sure what you told is correct or wrong?
So denser to rarer, sir.
That is what the case is. The light to travel from where?
Denser
The light
to
should travel from denser medium to rarer medium. Okay. So that is what, when a ray of light traveling from denser medium to rarer medium, right? When a ray of light traveling from denser medium, that means light should travel from denser medium to rarer medium. Okay. Right. Of course, this is a normal. Okay. When a ray of light is traveling from denser medium to rarer medium, it reflects back into the same medium. It reflects back into the same medium. Okay, so this phenomena of reflection of light back into the same medium is called total internal reflection. I'll tell you, I will show you some points behind that. Okay, so that is what, when a ray of light travels from optically denser medium to rarer medium, right? The light is getting totally reflected. The light is getting reflected back into the same medium. Okay, then we can tell that light is total internally reflected, right? So that is the basic principle. I'll show you how the light will get reflected, because we have so many parameters. So light traveling along the the light traveling along the normal, okay, light along the medium, right? That is what, along the 90 degrees, where we find some critical angles and all. I'll show you, right? So beyond that, before that, let us discuss some of the contents that are to be covered here, right? So that is principle and construction of optical fiber, acceptance angle, numerical aperture, right? So that there are different types of optical fibers called single mode, multi-mode fibers, and step index and graded index, and optical fiber communication systems with some block diagram. And we shall see also the applications of optical fibers, right? Now let us see. So fiber optics is just we'll see some of the fundamentals. Okay, we'll see some history and all. So fiber optics is a branch of physics based on the transmission of light through transparent filters of glass or plastic, right? So optical fiber is a cylindrical or transparent dielectric medium designed to guide visible and infrared light over for a long distances. So optical fibers works on the principle of total internal reflection. That is what we have seen. That is, when a ray of light travels from denser medium to rarer medium, right? And if the angle of incidence is greater than the critical angle, then light gets totally reflected. So this is what we need to understand. So this is what basically we need to understand. That is, when a ray of light travels from denser medium to rarer medium, as I told you, when a ray of light travels from denser medium to rarer medium. So this is your air and this is your glass. So this air is your rarer medium and glass is denser medium. So here light is traveling from where? Light is traveling from glass to air medium. That means light is traveling from denser medium to rarer medium, right? So when a ray of light travels from denser medium to rarer medium, and if the angle of incidence is greater than the critical angle, so where can we have the critical angle? So before knowing what is critical angle, let us see the figure that is established over here, right? So we have the glass. From the ray of light is traveling from glass. Hey, Babu. When a ray of light is traveling from glass to air, right? So the light is reflected here, right? So this is what we call it as refraction. So that is what, if the angle of incidence is less than the critical angle, then light refracts away from the normal. So this is your normal. So light is refracting, away from the normal, making some angle, some R, right? But in this case, if the angle of incidence is equal to the critical angle, in the angle of incidence is equal to the critical angle, then a light refracts at 90 degrees to the normal. So this is your angle of refraction here. That angle of refraction is observed in rarer medium, right? Now, if the angle of refraction is along the plane, that is, if the angle of incidence is equal to the critical angle, then the light refracts at 90 degrees to the normal. Okay, so this is what the 90 degrees we can see here, right? So here the refracted ray is making 90 degrees with the normal. So the refracted ray is making 90 degrees with the normal. Okay, so that means if the angle of incidence is equal to the critical angle, the light refracts at 90 degrees to the normal, right? So if you see the third figure, the same, we have the optical rarer medium and other is the denser medium. This is glass and this is air, right? The angle of incidence is greater than the critical angle. Here if you see, here the refracted angle is equal to the critical angle. Here it is 90 degrees, right? So here it is beyond the critical angle. That is what we are writing. If the angle of incidence is greater than the critical angle, then total internal reflection occurs, right? So this is what the refracted ray, this is what the critical angle, and if the angle of if the angle of refraction is greater than the critical angle, then lights get internal reflection. Light gets internal reflection. That means internal reflection occurs into the same medium. Internal reflection occurs into what medium? Same medium, right? So this is what the criteria is, right? So again, I'm telling you, please listen. So the principle of working of optical fiber works on total internal reflection. So the total internal reflection can be understood by taking the media, right? One is the optical rarer medium and there is optical denser medium. When a ray of light travels from optical denser medium to rarer medium, right? So the light refracts in the same medium. Okay, the light refracts. Okay, in one case the light refracts into the rarer medium, right? If the angle of incidence is equal to the critical angle, then light refracts at 90 degrees. Light refracts at 90 degrees to the normal, right? If the angle of incidence is greater than the critical angle, then light gets total internally reflected. So this phenomena is what we use for the principle of optical fiber. So optical fiber works on the principle of total internal reflection, right? Clear? Is that clear?
Yes, sir.
Right. Now let us see the principle and construction of optical fiber. Okay, so in optical fiber, so we have in optical fiber we have different parameters for optical fiber. They are core. First one is the core, other is the cladding, other is the silicon coating, other is the buffer jacket, and strength members and outer jacket. So these are the different. Okay, so these are the different forms of optical fiber. I'll show you one more. Okay, so so what is a core? This is your core part, right? So this is your core. Can you see here? This is your core. The very front part is the core. So it is made of, it is a typically cylindrical glass material. It is a typically cylindrical glass material of diameter 50 micrometers surrounded by cladding. Okay, cladding, you can see there the red part is nothing but the cladding. Okay, so cladding is nothing but a glass material of slightly lower refractive index than core, right? The core and cladding, the refractive index of cladding is more when compared to the refractive index of the core, right? So it is provided a silicon coating is provided between clad and buffer jacket in order to improve the quality of transmission of the light, right? A silicon coating jacket, okay, a silicon coating is provided between clad and buffer jacket in order to improve the quality of transmission of the light, right? Another one that is uncovered is the buffer jacket. Buffer jacket, it is covered over silicon coating, which is made up of plastic material and protects from moisture and abrasions, right? So this is what regarding the buffer jacket is. So other is the strength members. Strength members, this layer is arranged over the buffer jacket to provide necessary toughness and tensile strength of the fiber. That means if you take a fiber and try to break it, or try to mold the fiber in different angles, right? So the strength member will try to protect that. Okay, so that means this layer is arranged over the buffer jacket to provide necessary toughness. That is what. Okay, and tensile strength to the fiber. And foremost, we have the outer jacket. Finally, a black. It is made up of a material called polyurethane. Okay, that's why we write finally a black polyurethane outer jacket to avoid damages during hard pulling, bending, stretching, or rolling of the fiber in the real field. So these are the different parameter. These are the different different parameters involved in optical fibers. That is core, cladding, silicon coating, buffer jacket, strength members, and outer jacket. So outer jacket, right? So these are the different material. These are the different parameters that are involved. Okay. Now let us see the principle. Let us see how the reflection and how the parameters, how the laws of refraction are involved, right? So we have here, we have the laws of reflection. That is, we know what is a Snell's law is. What is Snell's law? Snell's law is what we can write it as the ratio of sine of angle of incidence to the sine of angle of refraction, right? You all know what is Snell's law, right? So this mu is nothing but sin I by sin r, we write generally, right? So this mu is nothing but the refractive index. Refractive index is nothing but the ratio of the velocity of light in one medium to the ratio of velocity of light in another medium. So that is based on that, the Snell's law can be written as mu is equals to sin I by sin r. Mu is equals to sin I by sin r. So based upon that, right? So just we'll see how the mechanism takes place. Okay. So according to law of refraction, n1 sin theta 1 equals to n2 sin theta 2. So if you see this figure, please, all of you, is the screen shared? Can you see it, all of you?
Yes, sir, we can see.
So if n1 sin theta 1 equals to n2 sin theta 2, right? So this is your denser medium and this is your rarer medium. As we have seen, when the ray of light travels from denser medium to rarer medium, right? So if the refracted ray will move away from the normal. So if you take that as angle as theta 2, and the angle of incidence between the normal in the denser medium is taken as theta 1, we can write the relation as n1 sin theta 1 equals to n2 sin theta 2. Right? So this is what our Snell's law we are acquainted with. We know what is Snell's law, right? That is what n1 sin theta 1 mu is equals to sin I by sin r. Sin I is taken as theta 1 and sin r is taken as theta 2. Right? Therefore, we can write mu is equals to sin theta 1 by sin theta 2. Right? This refractive index is nothing but the ratio of the velocity of light in one medium to the velocity of light in another medium. So in that scenario, if you write mu is equals to sin I by sin r and mu is the refractive index n1 by n2 or n2 by n1, we can write n1 sin theta 1 equals to n2 sin theta 2. Right? Clear? We know that what Snell's law, right? You all know Snell's law?
Yes.
So mu is equals to sin theta 1 by sin theta 2. Okay. So this is mu. So this is n2 by n1. So this refractive index mu is nothing but the velocity of light in one medium. That is what we can write it as n2 by n1. n2 by n1. So if you cross multiply this relation, you get n1 sin theta 1 equals to n2 sin theta 2, right? So if you apply the conditions, that is, if theta 1 is equals to theta c, which is greater than if theta 1 is equals to theta c, that is theta 2 is equal to 90 degrees, then we can write, so the critical angle theta c is equals to sin inverse n2 by n1. As there is no loss of light energy during reflection, optical fibers are designed to guide light wave over long distances. So the why here the condition to understand is why the optical fibers are designed. Okay, why the optical fibers are designed, okay, to guide light for a long distance. So the explanation or the physical phenomena or the mathematical case which can be explained is by using the law of refraction. So that is what the case we have wrote there. That is n1 sin theta 2 is equals to n1 sin theta 1 equals to n2 sin theta 2, right? If theta 1 is equals to theta 2, that is theta 2 is equal to 90 degrees, right? So sin n1 sin theta c is equals to n2 sin 90 degrees. Why sin 90 is becoming there? Anybody can explain why it is becoming 90 degrees there? Because why it is becoming 90 degrees here? Why the case is becoming 90 degrees here, theta 2? Why theta 2 is becoming 90 degrees? See here, this is theta 2, right? This is theta 2. So here, if the angle of incidence is more, then refracted ray, instead of going like this, it is becoming perpendicular to the normal. Okay, so that's why theta 2 is becoming 90 degrees here. Do you understand this point? Why theta 2 is equal to 90 degrees? Here theta 1 is equals to theta c, right? Here theta 1 equals to theta c. Am I right? Yes.
Yes, sir.
So here theta 1 is equals to theta 1 is equals to theta 2 ఎంత అవుతుంది బాబు? Theta 2 is becoming 90 degrees here. So because the refracted ray is becoming perpendicular to the normal. Okay, therefore theta 2 is equals to 90 degrees. Therefore n1 sin theta c, when theta 2 is equals to 90 degrees, then we are telling that the angle is the critical angle. Okay, that angle where the refracted ray becomes 90 degrees. The angle where the refracted ray becomes 90 degrees is called the critical angle. So that's why we are writing theta 1 is equals to theta c. Okay, therefore n1 sin theta c is equals to n2 sin 90 degrees. Okay, therefore we are writing sin theta c is equals to n2 by n1, that is theta c is equals to sin inverse n2 by n1. Okay, so this is the condition. The purpose of introducing optical fiber is, as there is no loss of light energy, during reflection. Okay, optical fibers are designed to guide light over long distances. Okay, so here theta 1, this is theta 1. Okay, and theta 2 is becoming theta 1 here. See, what is theta 2? Theta 2 is the angle of refraction. Okay, so the angle of refraction is becoming theta 1. That means the light is internally reflected into the same medium. Clear? That is why we write theta 1 is greater than theta c. Okay, this is what we understood here, right? This is what we have seen over here. Am I right? This is what we have seen over here or not? Is that okay?
Yeah, sir.
Is it okay to all of you?
Yes, sir.
So please try to understand what is the principle of what is the total internal reflection. If you understand, the remaining everything will be easy. So what is total internal reflection? That is what the fundamental point we have to understand here. Then we can go for different characteristics of optical fibers. Yes.
Yes, sir.
Can you see me? Is my voice audible?
Yes, sir.
Yes, sir.
Okay. See, just see here. So let us see some of the important let us see some of the important concepts of optical fibers. Okay, so that is what introduction to fiber optics. Okay, fiber optics or optical fibers. So till now we saw what is the principle behind the optical fiber, that is the critical angle and total internal reflection and all. Now, and also we have seen what are the different types of materials that are surrounded by a fiber, that is core, cladding, okay, silicon jacket, buffer jacket, okay, strengthening the material. So sorry, strengthening the material of the fiber. Okay, so what are the different parameters and all we have seen, right? Now let us see. So optical fiber is a flexible transparent fiber made of extruded glass material, that is called the glass material is called the silica or plastic, slightly thicker than a human hair, right? So it can function as a waveguide, that is what it is used as a transmission. Okay, transmission of wave, transmission is what we have seen. Okay, so that is what we have seen, that optical fiber is cylindrical transparent dielectric medium to guide visible and infrared over long distances. Okay, so based on transmission of light through the transparent filters or glass or plastic, that is what we have seen. Okay, so it can function as a waveguide. It can function as a waveguide. That means it can be used as a transmission of signals from one point to another. Okay, or light pipe to transmit light between two ends of the fiber, right? And other is the power over fiber. Power over fiber optical fiber cables can also work to deliver an electric current for low power electrical devices. So this power of over fiber is not there, but it's included in some part of optical fibers. Okay, so let us see. So optical fibers are widely used in fiber optic communications, where they permit transmission over long distances and at higher bandwidths. Okay, rather than higher bandwidths, so that may than the wire cables. So fibers are used instead of metal wires, because signals travel along them with less loss and are also immune to electromagnetic interference. So fibers are also used for illuminations and are wrapped in bundles so that they may be used to carry images. Okay, so that is what the structure of an optical fiber. As I told you, we have different parameters there. So that is what core, cladding, okay, buffer jacket, the coating materials, buffer. Okay, so let us see. The structure of an optical fiber consists of three parts. So the core and the cladding and the coating, as I told you, or buffer or outer jacket. Okay, so it has own different parameters. The fiber is around, the thickness is 7 to 10 micrometers, and the cladding, the diameter of the cladding is expected to be 125 micrometers, and the buffer is having the diameter around in the range 185 to 700 micrometers. So this is what the buffer means. It is nothing but the just cover chese material, right? So the cladding ni cover chese the buffer, right? Core ni cover chese the cladding. So, and we also came to know that one point, that is the refractive index of core is very much less than the refractive index of the cladding, right? So that is the important, that is also one parameter which you need to understand. So the core is cylindrically rod of dielectric material. So light propagates mainly along the core of the fiber. The light travels in the core, right? This is the core. So this is the core. Light initially enters into the core. Okay, light initially enters into the core. That is what light propagates mainly along the core of the fiber. The core is generally made of glass. The core is generally made of glass, and the core is described as having an index of refraction N1. So the refractive index of core is N1. Okay, the refractive index of the cladding is N2. So the refractive index of the core is N1 and the refractive index of cladding is N2, right? So the core is surrounded by a layer of material called the cladding, okay, which is generally made of glass or plastic. So the cladding layer is made of dielectric material with an index of refraction N2. That means the cladding is having the refractive index N2. So the index of refraction of the cladding material is less than that of the core material. Okay, that is what the refractive index of cladding is less than that of the core. Okay, so remember this. So the cladding performs the following functions. So the performance, right? The cladding performs the following functions. Okay, so it reduces loss of light from the core into the surrounding air, reduces scattering loss at the surface of the core, and protects the fiber from absorption from absorbing surface contaminants, and also adds mechanical strength to the fiber. Okay, so these are the functions of the cladding. So cladding functions, the function of cladding is to reduce the loss of light from the core into the surrounding air, and reduces the scattering loss at the surface of the core, and also protects the fiber from absorbing surface contaminants, and also increases the mechanical strength, right? And buffer, as I told you, buffer is nothing but the outer layer. The buffer is nothing but the outer layer of the fiber. Okay, the coating of our buffer is a layer of material used to protect an optical fiber from any physical damage. That means, see, that means if you try to twist the fiber, okay, so there is some there may be some damage happens into the copper wire inside the fiber. So in order to retain the shape and size of the optical fiber, okay, so buffer is surrounded. Okay, buffer protects the fiber. Okay, that is what the coating or buffer is a layer of material used to protect an optical fiber from physical damage. So the material used for buffer is a type of a plastic. So the material used for buffer storage buffer is a type of plastic, right? So again, we have seen what is the principle of optical fibers. So total partial reflection, critical angle, and total internal reflection. Okay, so other is the critical angle, that is the same when the angle of refraction, okay, when the angle of incidence is increased, angle of refraction also increases, and the stage is reached where the refracted ray just grazes the surface of separation of core and cladding. At this position, the angle of refraction becomes 90 degrees. So this angle of incidence is called the critical angle theta c of the denser medium with respect to rarer medium. If the angle of incidence is further increased, then the ray is totally reflected. This is called total internal reflection. So how the light is getting internally reflected in the fiber is what this slide is, right? So when a light ray traveling from optical denser medium into an optical rarer medium is incident in an angle greater than the critical angle, then the ray is totally reflected back to the same medium by obeying the laws of reflection, right? So reflection laws, you have studied in your lower classes, that angle of incidence is equals to angle of reflection. The incident ray, normal, and the refracted ray all should lie in the same plane. So this phenomena is what we call it as the total internal reflection, and those above said are called the laws of reflection, right? So this is what the light is. See, this is your light propagating into the core part of the fiber, right? So again, the light is getting totally internally reflected. The light is internally, reflection takes place. Okay, so here this part is nothing but the core, which is provided with higher refractive index. The refractive index of core is greater than refractive index of the cladding. If you take N1 as the refractive index of core and N2 as the refractive index of the cladding, you should have N1 is greater than N2, that because the refractive index of core is greater than the refractive index of the cladding, that is N1 is greater than N2. Right, so that is what the total internal reflection. So this is what the condition for total internal reflection, right? So these are the some of the basic parameters. So these are the some of the basic parameters which you need to understand while studying a optical fiber. Okay, any doubts? Any doubt?
No, sir.
Any doubt? If you want, you can write this. This may become some important. This may become some important and make some sense for you. And we need to go for other topics, that is called acceptance angle and acceptance cone. So this all will study tomorrow's class. So just let me know if you have any difficulty in understanding this. Yeah, tell me first. Nothing, just we need to understand what is total internal reflection, right? If you understand what is total internal reflection, you can see how the light is getting internally reflected. Okay, so for the light to get internal reflected, the incident angle should be greater than the critical angle. This is what the point which you need to understand basically initially. Okay. Any more doubts? So this is what the core, if you see the if you see the structure of optical fiber, okay. So if you see the structure of optical fiber, we have initially we have the core material. Core is made up of silica and is surrounded by cladding, and cladding is also a material made of silica, okay, and it is surrounded by silicon coating, okay, silicon coating, okay. You can see optical fiber cables everywhere, anywhere you can see. If you just see, especially they are used for communication purposes, okay. So for telecommunications and all, they use some optical fibers, and this core cladding is surrounded by some buffer jacket, okay, to protect the layer, okay. And it is again, this buffer jacket is further protected by strength members. So strength members in the sense, though we apply a lot of pressure on the fiber, the core and the cladding and all the parts, all the parts of the fiber should remain unchanged. So that is what. So the strength member, that's why this layer is arranged over the buffer jacket to provide necessary toughness and tensile strength to the fiber. Okay. So this strength members, these members are used to make the fiber toughen. To make the fiber toughen, though we apply a lot of pressure on the fiber. So these strength members will protect by giving necessary toughness, okay, and tensile strength to the fiber. And it is and the last one is, it is surrounded by some black jacket. So that means there's a black layer, right? If you see here, if you see this, right? So this is what the black, okay, this is what the black part we have. This is what the black part, okay. So black part, we have some core, cladding, core, okay, all these features, okay. Cable ki black etla untundo baita surface, so that is what the black jacket. So generally, so the materials made are the material made for making the outer jacket, that is black, is nothing but what is that material? It is a black polyurethane. Polyurethane is the material that is used to make the outer jacket as black. Okay, the black outer jacket material is polyurethane. So that is what the outer jacket. So this is what basically we need to understand regarding the principle and construction of optical fiber. Okay, and tomorrow we'll see what are the parameters that are required. Okay, what are the parameters that are required? How we need to understand the acceptance angle, acceptance score. So I think we have studied in our physical lab. In the lab, we have studied the numerical aperture of an optical fiber. Have you studied or not in the previous lab? In the previous lab, we have gone through the numerical aperture of optical fiber. Have you seen? I think we have done it. I think we have did it in our previous lab. Am I right?
Yes, sir.
Previous lab lo chesam kadandi manam. Okay. So this is what we have to understand regarding the optical fiber, and tomorrow we'll see what are the parameters and what is acceptance angle, acceptance cone, okay, and how the relation between the acceptance angle and acceptance cone. And we need to see the different mode of fibers, that is step index, graded index, okay. So, and we need to understand the differences between the modes of fiber, that is how we differentiate between step index and graded index, single mode and multi-mode fibers. Okay, if you have any doubt, can please get it clarified. Is that clear to all of you?